Hi, everyone. Good evening, and welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Batum with Atlanta Functional Programming. Last week, we covered the third part, major part of our discussion on efficiency issues, which is Chapter 9, specifically the topics of profiling, deferring the discussion on indexing until today. And today we're going to be finishing up one small bit on our unprofile macro that was shown last stream that I ended up realizing was actually a typo on mine, and I'll explain in a minute. And after that, we're going to be covering a bit of a case study on improving the efficiency and at least looking at techniques of improving the efficiency of the Simplify program that we were studying in Chapter 8. Before we begin, a couple of announcements. As usual, Atlanta Functional Programming is a meetup that encourages the use of the functional programming paradigm, has kind of a core paradigm in building large-scale software systems. We normally have talks at least once a month, although we are now in dire need of speakers. For those of you who are out there in YouTube land who are interested in speaking as part of the Atlanta Functional Programming, feel free to reach out to me. I am Bugram on the Functional Programming Slack channel, and for those of you who are in the Atlanta area, feel free to send me a DM on Tech404, which is Atlanta's premier uh, Slack workspace for the tech community, and we will get you scheduled into our, agenda or speaker agenda for the coming months. Uh, Also, for those of you who are in the Atlanta community and in the Atlanta area, uh, Atlanta Functional Programming is in dire need of a new home for in-person meetups. We do periodically meet up at various coffee shops and stuff, but we would like a more permanent residence to provide more formal talks. For those who have suggestions, also DM me or my co-organizer, Judd Taylor, on the appropriate channels in Slack and or even meet up directly, and we will try and coordinate with you to make sure that we can, set up a time to actually go and meet up and view the space and so forth. Uh, those of you who are in YouTube land also, before we begin, if you like our videos, please like and hit the subscribe button or the bell icon to allow yourselves to get notifications whenever new streams come up, new topics come up, as well as small tidbits and talks. In the coming weeks, we will be discussing other topics as well for those who are in the YouTube land. It's just I'm trying to coordinate and get some time to actually go and prepare some of that material. And when that comes to fruition, I will present it. But in the meantime, do enjoy our weekly Common Lisp Study Group streams. And for those who haven't joined us until recently, we do have all of our streams located on our YouTube channel. So not only subscribe to the bell icon, please visit our YouTube channel to view past episodes of the Common Lisp Study Group. And provide some feedback in either in the comments of this video or in those other videos, and we will address them as we see them. So last time when we talked about profiling, we uh, introduced you to this example that was kind of published in the book, where we have a function called profile1 that kind of gave us a basic idea of profiling or generating a profile inside of Common Lisp, specifically focused on the number of times a particular function may have been called. A lot of other languages tend to have similar infrastructure, but in many cases, especially when you're coming from the statically compiled world, oftentimes it's the case that you end up having to add that profiling instrumentation from within the compiler in order to encourage a more uh, what would be the best word for to say this? A more rigorous, more accurate profile of the execution that would occur for that statically compiled language, especially when you start talking about languages where they aggressively optimize when compiling high level code. So you can actually get some more definitive statistics. In Common Lisp, you don't necessarily need to do that because you have the ability at runtime to provide metadata information to the Lisp runtime to actually in a non-intrusive way get statistics when a particular function gets called. And as we could see in this case here, what we've done is we leverage the associative list that is typically provided for any given symbol that is defined to actually get the symbol function and um, add metadata to that symbol related to the symbol function. Specifically in this case, as you see, when we actually go and do profile one, we add metadata to make sure that when we call profile one, we know what the actual function pointer, the original function pointer was. This is so that when we finish profiling, naturally we want to stop profiling, so we'd have to be able to return it back to its original state. So we're able to keep track of that along with the counter so that we can actually provide reporting statistics. You can also see that this has being some way of providing timing statistics if you end up wanting to by getting the time at which a particular function gets started, and when the function is about to end, you can add additional information to get how long a particular function has taken and reporting that as part of your profile report. Either way, the standard technique is somewhat the same in that you just add this metadata to the symbol, and then when execution is complete, you can actually take that collected information and provide a standard report, which we showed you when we actually took um, the count that we provided a nice convenient function there on line 23, and we created the profile report inside of the book, from the book, using the profile count. And this just simply went through all the function names and it sorted it in descending order. And so you knew what the highest counts were before the lowest counts. So this will give you essentially effectively a descending report and provide you to identify bottlenecks much quickly. We also introduced you last week to two profiles Dr. Norvig created, profile and unprofile, which I named is for to prevent collisions with CL profile and unprofiled macros that's defined in the standard with M profile and M unprofile. And these basically essentially calls the profile one function that we've defined. So this way you can actually extend this to check to see if a particular profile function is already being profiled, so it doesn't go and try and profile it again. You can also deal with redefined functions by taking a profile out and updating the unprofiled function pointer with the new profile function pointer. These sorts of stuff can occur when you have this kind of macro and you could do some sort of macro generation. Additionally, we ended up introducing you to M unprofile, which also goes through and does the opposite. And we hit the situation where when we tried to hit unprofile, we ended up getting the follow macro expansion that we were actually oh, sorry, I'm showing you the after. Um, the macro expansion of this is basically something that we saw like this. Okay. As it turns out, the reason why this was occurring, okay, and again, the reason why this is wrong is because, as you can see on line 65, what we should ultimately get is a list, but the list that's being passed on line 63 to mapcar isn't actually technically a list. It's an S expression that looks like a function invocation in Common Lisp. It needs to be quoted, otherwise you're going to have some problems. Now, the way to fix this is not, to say, quote, um, is one of two ways. And I'm going to probably show you, I'm going to try, I didn't try this before, but I'll show you the one way that I was thinking about of trying on air, which is basically wrapping this guy in a quote, a legit quote like this, which I believe should work. And we could actually see here um, when we do a macro expansion. Um, yeah, it doesn't work. It's because of the fact that at the end of the day, this guy here is still not treated as a list. So if we do this, we'll see that this becomes an error. Okay, and this is kind of the error that we were seeing before too as well, that we're using a comma in we're using comma and unquoting an expression that's not within the back quote. So I'm going to explain that in the macro expansion here as I go and fix this. First, let me do this. I believe I have a connection here. Okay, good. Um, so the reason why that error was occurring, and let me first undo this and show you what was happening, is because while we are technically in a top level quote here, remember macro expansion rules, right? Anytime um, there's a back quote, you only need to unquote once to actually go back to kind of the evaluation stage, right? And we've actually technically unquoted the expression and the nested tree, if you will, the subtree, on line 49 when we unquoted if, right, to actually check to see if we have an empty level stuff. So we can't just simply quote comma like this to actually get the list, right? What we have to do is we have to first re-invoke the macro expander, all right? And by doing that, and this is where my mistake was, um, you have to back quote the quote, and then you can write comma function names here. Now, the book had this, but it looked like when you look at the typesetting there, that it was two single quotes, which is wrong. It's actually a back quote followed by a single quote and then a comma. So I would have ended up. So I'm going to show you what this looks like, and then I'm going to show you that you can actually also write what I did earlier with quote this way too as well. So just give me a second here. Um, do that. Save. And then if we go and look at now our profile, we could see that we actually get the appropriate macro expansion that we wanted, which is the list of the symbols that we want to go into call profile on. The other way of doing this is naturally, if this is somewhat jarring to folks who aren't used to it, and again, this for the time being, when you're writing code, you could certainly do it this way, although this is kind of standard practice. Once you get to a level of comfortability with coding, you could certainly wrap this by saying back quote, open paren, quote, comma, this. And this also would be the same thing, except instead of now doing back quote, quote, you are just calling the function directly. And you can see that it's the same thing. It'll eventually get expanded to the correct thing that we saw earlier. Okay. Okay. As you can see right here. Okay. Now what we could do here is just to show you the start of this. If we start profile, let's go ahead and start our profile. Okay. Okay. We check our initial profiling report to show you that this is all reset. And if we end up calling test profile, which is our kind of basic thing here 100 times, and then we run our profile report again, you can see that this is now our profile report. And if we call mum profile test sum 2. Okay, and we run profile report again. You can see that everything got reset. Okay. Now some of you may be wondering, well, I see that when we run um, unprofiled, technically the information still exists in the associative list. Um, while that is true, as far as I know, there isn't any, at least from my experience, there isn't any. Once you add something into the metadata table, I haven't seen a way to actually get that information out other than reset the key. But that's only because my knowledge of the get was just more recent. But we could go and look at the hyperspec too as well to remove it if we want to be completely cleaning up after ourselves and making sure that all the metadata is completely removed when we start unprofiling something. Um, this is just a small optimization when you want to add metadata. Um, so, um, so hold on one second. Let me just take a look at this. Get properties is all properties at once of a val. Um, you create a prop one, prop two, get f nil. Right. So if we do, so there's a couple of things here that I'm going to just show you too as well before we move on, which is with this information, you have something called get properties um, in here, and on, let's say, the function name, which is test sum, and then our indicator list is just, profiled function and profile count. And what this does is oh, it's not even in there. One second. My apologies. I have to actually put, thought it was get properties, place indicator list, right? Oh, my apologies. I should have said, um, instead of that, instead of coding it, I need to say place. So it's the symbol itself is what we want, right? Test test sum is unbound. What are you talking about? One second. Oh, this is only dealing with property lists. My apologies. I'm looking at the wrong thing. Um, Here you go. Get. Uh, Get finds a property on the property list whose property indicator is identifiable to the indicator. Okay. Um, yeah, I think what we have to do is just simply to get rid of um, the, uh, the the properties. We need to call Yeah, we need to call maybe remove prop from the symbol. Yeah, that's what we need to do. So there's a function called remove prop in the standard for dealing with metadata like this. And I'm just going to show you this. What this does is uh, uh, and what this does is it basically takes a symbol indicator and then just simply removes it from the property list. Okay. What's interesting though is I was under the impression. Oh, maybe I have to do that. Okay. So just like get properties is for a p list, all right, which is I was using the same thing. I was assuming that it was the symbol was a p list. There is actually a way to look up the symbol p list because this is a structure, right, that we saw earlier. So we can use symbol p list, okay, on the symbol like test sum to actually look at the p list that we've created here. All right. Notice that the symbol p list is still there. What we did before is in unprofile one is we just simply reset this information. But what we really want to do is we need to, when we say unprofile, we should get rid of these information. Yes, because of the fact that the metadata isn't going to be clean, number one. Number two, if we redefine the function when you unprofile, okay, um, what you should really be doing is not just look up and then reassign, because that can do it because garbage collection can actually go in common Lisp to get rid of the unused garbage thanks to the ability of you know uh, anybody who's done stuff with garbage collection. If there aren't any references, it becomes garbage. It gets labeled to be garbage. In the next garbage collection cycle, it gets removed properly and deallocated. We could force this and by just simply not only do the result stuff here, okay, we can also make sure that here we remove um, here we could do something like this first if we wanted to as a first pass. Okay, unprofiled function and um, nil. Okay, and then what we do is this will also work on what we did earlier. Hold on, let me just show this. If we run our unprofile here and we run symbol plist, we could see that everything is properly nilled. And then to really clean up, we could get rid of those from the symbol plist by just using remove property. Okay, and remove property will naturally then take the sorry, we have to first provide the function name and the symbol that we're trying to grab, and we can just go ahead and run this. Oh, sorry, my apologies. My autocomplete is messing with me today. Okay, and we could also call remove prop, the symbol on profile count, and this here will grab done. All right, and that would um, handle these other cases. Okay. All right. So now when we do this and we call unprofile, you'll see that if we call it twice, nil is not of type function, right? So it means it doesn't exist. And we could also verify that by just calling symbol test sum. Ooh, wait a second. Oh, my apologies. Let me call this first, just so that we can actually set the symbol list to being nil, not nil. Um, so we have a function here, and if we call this correctly, call this, you can see that everything got properly removed and cleaned up. Okay, so now we have a correct framework that loads and unloads everything, gets rid of it, everything is pristine. There isn't any unused variables inside of our symbol list. Well, there wasn't in the first place, by the way. When we set that nil, we actually cleaned up all the garbage, but technically we put in defaults. These keys should not exist when you're done. In production code, it shouldn't turn out you shouldn't leak some of that information because that is technically showing people if they end up knowing Common Lisp and let's say you didn't say unintern symbol plist when you were submitting your production code, um, they can actually go and check out what was done and what was not done. And you want to make sure that a lot of those frameworks are cleaned up. So this is our basic um, uh, framework for profiling stuff. Before I move on to the next section, are there questions? Okay. So the next topic that we're going to be talking about is the the case study related to um, Simplify. Okay. Now I want to first quickly review, like in a few minutes, and I'm not going to go through a whole episode on this just because we've actually covered this. But if you go and look at um, Maxima and remember what our simplification tool was. Okay, for Maxima. Okay. Um, Maxima was a system that basically, um, it does symbolic computation. And the Maxima program that was written as part of Chapter 8 was kind of a very simple implementation of what Maxima actually can do. It doesn't do just it doesn't do everything that the core Maxima does. We will cover something like that that has a different algorithm that could do more than what this is being presented. But this simplification algorithm implements the same pattern that we've been actually discussing in the last 4 or 5 systems that we looked at, from GPS through ELIZA and so forth. So this does the search space. It actually looks up the particular rule to actually go and do the simplification, and we have a simple example, a simple function that goes and calls the actual expression that provided the input that was provided. Okay, so naturally, one thing that should come into mind to any person that's uh, wanting to speed up this kind of program is, what sort of techniques can we actually go in and use? And we've already kind of introduced a lot of these throughout this chapter. Uh, Memoization was one. Compiling, we saw compiling in when we were looking at sentence generation and the sentence program that we introduced in chapter two when we were studying chapter two. But indexing we didn't really talk about because indexing required some more of a thorough example in order to really discuss it. So let's, briefly, let me explain what the indexing stuff uh, is uh, is talking about, or at least let's cover the basic examples of what indexing is about inside Common Lisp. Everyone knows that the basis of Common Lisp, because of its name, is the list. All right. Lisp originally stood for list processing. All right. It's the list processing language. Okay. So list was the universal data structure that Lisp was built on. Okay. But it turned out that lists were far more versatile than most people realize because you could literally use it to represent sets, ordered sequence. You could also hold lists of lists, which allow you to represent trees and graphs and even graphs with cycles and so forth, right? So when you were building large scale systems, or even let me, let's ignore large scale systems, small to medium scale systems, all right, where you could rapidly prototype and create quick programs. This um, it was easiest to represent this data in the list and get the program out the door. But anybody who's written their own list implementation, okay, linked list implementation, all right, which Lisp is built off of, knows that you're dealing with pointers there, and every level of pointer indirection um, increases the uh, inefficiency of the program just because there's a potential for you having to actually reach out to memory in various shapes and forms. I'm not going to go through the discussion on cache hits and cache misses and stuff, but most of you are probably familiar with that idea. Uh, um, for those of you who are not, I encourage you to actually, and I may actually end up doing this in Common Lisp too as well. There is some very good books on data structures in Common Lisp that we can actually cover. Um, that also covers this material very nicely. But the idea is basically that a pointer inefficiency is pointer indirection will actually increase the inefficiency of a program over time. Okay. For small lists, it doesn't actually show, it's kind of menial, but as the list gets bigger, it will actually potentially be inefficient depending upon how often you have to reach out to memory to actually get information to compute something. Okay. So while it is true that lists, association lists, and all the variations of data structures can be modeled with lists directly, it's generally not a good idea, right? So Lisp actually provides other data structures, and we covered other data structures that it provided in various episodes when we actually introduced and started covering the Common Lisp Study Group over the years. And of these, everyone knows that there are vectors, there are hash tables, and so forth. Um, but what most people aren't aware of, or some, unless you're very well versed in Lisp and stuff like that, is in general some of the data structures that were designed in Lisp proper and Common Lisp proper when the language was released, they were built on very general ideas, and they themselves could be potentially inefficient. All right, and if you know for and for some cases it might be better to actually build your own data structures. The example that Dr. Norvig brings up, and I'm sure there are actually very efficient data structure libraries out there that implement this. Suppose you have a use case where you want to build your own hash table where you don't need to delete elements. All right, you could then use a different hashing scheme than the default hashing scheme that's actually provided in the Common Lisp hash table implementation. Rather than replacing it, you would ending up implementing the same sort of retrieval mechanisms that the current hash table presents. So you can actually leverage potentially some of the higher level functions that were built for hashes. Um, so we're going to be covering some of that in the topic today. Uh, the thing though to recognize though when you're talking about some of these optimization techniques, whether you're dealing with indexing as we just briefly explained here, or in the case of uh, what's it memoization, which we covered in compiling, is what ultimately are the bottlenecks that you need to fix. Okay. um, and again, when we're talking about indexing for a data structure, whether it be hash tables, vectors, property lists, and trees, asymptotic analysis of actually accessing that particular element is very important to understand. And obviously, when you're dealing with insertions versus actual retrieval, there are certain things that you might want to be aware of, particularly again when we're talking about deleting elements, is how do you quickly compute the place where you need to store something? It becomes a question, right? So the first thing we need to talk about on in regards to then improving the simplified program that we talked to is first defining the benchmark, right? If you're not aware of benchmark, it's just a simple test suite that represents the kind of workload that you're trying to run as fast as possible. Okay. The book actually has the benchmark that we're going to probably cover today. The first thing is obviously, let me go back and let me set, let me clean up our current exercise. Give me just 1 second here. Okay, so let's first load up PAIP. And then naturally we need to go into, as many remember, into the PAIP package to actually access requires, and then use requires to actually go and load in maxima r. And then we have everything kind of loaded now. Okay. Um, I'm going to create a scratch buffer for this just because this is really not something that um, the program kind of introduces. And then I'm just going to go ahead and paste the basic example that was provided here. Obviously, I need to simplify. I need to clean this up because unfortunately, um, some of this stuff is spaces should not be there. So we need to kind of get rid of some of this stuff. Unfortunately, for those of you who are watching, this all is the result of me grabbing the example from my PDF copy of the book that I generated from Norvig's code online. Um, and for those of you who are interested in that, it's just a simple pandoc that I ended up doing on top of his markdown to actually get the resulting PDF, and it kind of worked. So So let me just double check here to make sure I'm not messing things up here. Um, Fix to prefix. Okay, ax squared plus bx. So the spacing here is fine. Let me get rid of that um, because it wants everything to be nice and tidy. Also, I need to get rid of this space here. And let's get rid of this and this. These spaces are okay. Um, ah, this shouldn't be a capital A. This is a caret. Sorry. There we go. That, because that's an ax squared plus bx plus c. And I'm guessing that should be a closed paren with no space. Yeah. Okay. Let's make sure here is also this, and this squared plus cx plus d divided by x to the fifth over dx. So this is just d by dx of these functions that we're actually going to be looking at. Get rid of this. Divided by dx, get rid of that. Those are also corrected. This, oh, that. Sine of x plus x. Wait, x plus x. Okay, got it. So this one correct incorrectly. X plus x. There we go. And it times sine of 2 times x. Okay, sine of 2 times x. Oh, wait, we need to have a space there because it doesn't like parsing that. It's cosine of the derivative of x squared by dx, correct? Yeah, x squared by dx. My apologies, folks, while I'm correcting this. This is just, we should have had this kind of prepared earlier, but I didn't realize I would get this many formatting issues. And this is squared to the 1. Okay. This, and that. And then what is this? 3x plus cosine x divided by x. Okay. 3x plus cosine x divided by x. Okay. 3x plus cosine x divided by x. Okay. Dx. Okay. All right. So this is all ready. Let me just quickly do this one. Okay. And oops. Okay. So a couple things here. Def bar is still fine for doing this, but if you're doing this today, I think the preference is if you're initializing a value, is use def parameter over def var. But def var is historically the way to actually define variables like this, so I'm not going to actually go and correct that. For those watching along, that's just keep that in mind. Let's go ahead and, oops, my apologies. Let's go ahead and grab this and load this up. There seems to be an issue with my form. here. Oh, I lost a symbol there. Good. All right. Okay. Now, oh, one more read error. Okay. Oh, okay. Done. Illegal expression. One. Def var map. What is the problem with this one? Let's see. We do this MCR. Okay, legal expression. What is the infix or prefix? Did this not get properly? Okay. So it's not liking something that was converted here when I copied stuff over. Give me a moment. Sine of x plus x. Sine of 2 times x. Okay. Let me do this. Let me get rid of the spaces here. Oh, no, not that. This. Okay. And see this. What is that? Alright, sine x plus sine 2 times x plus cosine of d of x squared by dx. Okay, so one of these it's not a fan of. See, x cubed plus bx squared plus cx plus d divided by x to the fifth. Okay, got that. Here we go. This is wrong. They added extra characters in. This is ax squared plus bx plus c divided by x. So let me just correct this. Divided by x dx, right? Divided by x dx. Yep, that's correct. Okay, let me just make sure this is all good. Ooh, that's not right. This is, okay, hold on. This here. Okay. I'm just gonna rewrite this this second one here, just because this is the one that's causing trouble. It's open paren ax squared plus squared plus b times x plus c. Okay, and then the whole thing here. Oops, that's not what I want to do. Fit with the whole thing here. Let's grab this. R divided by x. This divided by dx. Now we're good. Okay. Okay, so let's see if this one works. Okay, this is good. We could now load the answers to MCR. Everything is good. So if we look at the answers now, just to let you know, this will be holding our answers for our benchmark, right? So we now have the simplification of everything. So one way to write this, okay, this benchmark is you could use any testing framework that's out there if you really wanted to. But one thing you could do is potentially you define a function called like test it that creates a test run, make sure that everything is correct and so forth. There are plenty of unit testing frameworks that give you some of this stuff. 5am is one of them. We covered 5am in the past. I believe there are some macros for with package iterator, so there isn't. You can you can certainly create a quick macro for like if profiling with profiling if you really wanted to actually generate some profiling data. The example that Tested has in the test run introduces this in the book. I'm going to actually, since we don't have that defined right now, I'm going to um, not actually set this pro flag that is provided as an optional here. Um, Optional with profiling. Profiling set to true. And mainly because of the fact that we don't necessarily have I don't necessarily have the ability to actually go and define that right now, just because it would require me to actually go in and um, essentially make sure that actually maybe I can try. We'll see given the time being. Let's first get this in. So this tested function basically from the book first grabs our answers um, from the actual timing of it. And so here what we do is if with profiling, since we've set it to true, we're just going to go ahead and say with profiling uh, pro profiling, and we're going to have to define all the stuff that we want to profile, which is the entire stack. That's simplify, simplify, simplify exp. Okay, pat match variable and variable p. Okay, and this guy is variable p, which is the predicate. Oh wait, pat match variable and variable p. Match variable, okay, and then variable p. Okay, so this is basically our stack. And once we do that, we just go through and we call map car, simplify on our test data. Okay, and this is what's going to happen here. or if it's not defined, if we don't have a width profiling function, which we could shortly define very quickly, we will define time permitting because we have 15 minutes left. We just simply call time, which is available to all of us in Common Lisp, and we just simply time the simplification. But remember, it's not just timing the simplification, okay? Here, the way this time works is we first um, uh, essentially do a we validate um, once we um, once we have everything, right? And then that's a very simple map C assert equal, which we'll define in a minute here, um, on the answers that we provided, well, that we created with the answers that were generated that we did earlier that we initialized. Okay. And once this is done, then we just return true. That validates that thing. Okay. What is the warning? Give me a second. Assert equals. Oh, assert equals hasn't been defined yet. So let's go ahead and define assert equals. Okay. Um, assert equals, anybody who's done their basic, you know, thing is just going to be a simple assert. Okay. If they're not complain if x is not equal to y. Okay. And the way we do that, there's a built-in assert function inside Common Lisp that we're going to use directly. We are going to check value equality, which means we're going to use equal. And if equal works, then we just simply turn into places x and y. Okay. And then otherwise, what we'll do is we say expect a to be equal to expected, sorry, expected a to be equal to tilde a, okay, and xy, okay. And here, I think, oh, sorry, not tilde a, back quote, end quote, and then here also we're going to do back quote and quote. Okay, done. Okay, so now this is compiled and loaded. This is compiled and loaded. We don't have width profiling yet, just because we can turn off the profiling later on. Let's just do test nil to being nil. And the width profiling stuff, actually, I'm kind of curious as to where this was coming from. Profiling. I thought profiling is there because describe profile. And let me actually spell C. Okay. PAIP profile. That is not what I want. I wanted CL profile. CL profile. Package CL. Just give me a second here. Let me just check something here. Describe profile. That wasn't actually loaded. There we go. So we're gonna have I'm gonna have to do some experiments here just to see what the width profiling macro would be, because that actually doesn't look like it's here, but it seems to be giving some pretty decent information. I think, did I accidentally forget to write this? Ah, that's the reason why I forgot to write this. The width profiling functions were from the previous section when we were talking about it. Okay, no matter. We do not need the width profiling stuff. I could show you um, uh, uh, very quickly what this looks like. Um, but basically, there is a more detailed version of the profile report that I'll touch base on next week, just so that we could close it out with a nice bow regarding profile times. But to show how this assert kind of stuff works, I'm just going to use nil, for example, to time it. So if we do test it nil, oh wait, first let me change back to PAIP because we have that defined in PAIP. This package, we do test init nil, and what we'll see is it will eventually get something like this. We'll see in our profiling report, you know, just how long um, this took, how many cycles it actually ran, and so forth. This isn't giving you much information. It isn't a kind of a proper profile. It's just a high-level benchmark. Um, This is actually fairly fast because, again, in Common Lisp, especially SBCL, everything is compiled, so this isn't going to really show us much. But uh, we can actually see um, uh, uh, we can actually see that at least that there is a normal um, uh, test run of 6.6 seconds. Um, and it kind of gives you an idea of how fast your entire program is. But without the more definitive profile, which you can add by adding trace mechanisms in here using the standard library, um, this this basic example is just, a high level illustration of how you might want to define a benchmark. Okay. Um, So one thing that was kind of brought up in this mechanism is just take an example of the rule that would generate. So the example that was brought up into is to simplify x plus x into 2 times x. All right. Um, the rule that transforms x plus x into 2 times x for the purposes of computing stuff, and we simplify the result, you need to go and re-simplify some of the components of this this underlying expression. Okay, so in this case, when we go from x plus x into 2 times x, we're simplifying x, which x could be itself a complex expression, and that could entirely be wasteful if you're doing it twice, right? Because x plus x is it is evaluating X, simplifying X, and then going to the next X before actually reducing it into what eventually being the same result as 2 times X, right? So this kind of wasteful computation we've seen before when we started looking at stuff like, Fibonacci and other stuff. So this is a clear indication that you could potentially use memoization, right? Um, I'm not, with the last 5 minutes left, I'm going to just basically introduce this, which is um, with memoization, it's really uh, dealing with hashing in the hash table. And the book kind of covers the equal hashing and non-reset hashing, and it'll tell you kind of the differences between EQ and EQ equals resetting, and the differences between the timing of it and the performance. Now, it is a bit dated when it comes to times today, because obviously, computers have gotten a lot faster in the last 35 years. So take what they have with a grain of salt. Don't use it has the general steadfast rule, because optimizations may have actually made these things so much faster. But in general, when you're talking about hashing and hash tables, knowing what type of equality operator and what type of stuff that you're doing when you're hashing something becomes part of the equation when you're trying to insert something into a hash table. Um, So again, I'm not going to necessarily cover um, the Memoirs simplified test example that was covered in the book, just mainly because there isn't really much that we would kind of show, other than maybe a timed example of you doing a map car after doing a simplification. But um, we this kind of requires us to first, remember, define memoize, and then deal with some of the hash semantics. Um, Another thing that we could do to uh, uh, deal with and speed up is rule retrieval. All right. Every time we actually access every rule inside of the rules database, like this, whether it be, and to give you kind of again, a simple example is this, which is the simplification rules. We're actually going through each rule every time. So there's a linear cost every time you actually go and try to access a particular rule to actually um, retrieve it and test against it, right? This is very inefficient, right? Because most rules could be ruled out if they were properly indexed, right? This is where indexing will come in. If there's a particular pattern that allows you to retrieve the appropriate rule for that simplification, then this becomes much easier. So um, you could simply have a separate list of rules indexed under each operator, and then it could then look up the smaller rules based on the appropriate operator. Um, that is something that we can probably cover in the next time, because this is requires a little bit more discussion. But this is basically nothing more than an improvement of rule retrieval. Okay. Um, so next time in the first part of next week, we will cover this last section, where basically we take our rules database, this database here that you're seeing on the right hand side, and we're going to write an expression that actually simplifies the rules and cover the simplification and regeneration of an indexed hash table that we could then use to actually go and retrieve rules faster. And then we're going to then run our benchmark to see how much we've actually improved the simplification program by adding indexing into it. All right. Um, Thanks everyone for joining. I hope you all enjoyed today's episode. Next week has same time, same place, 8:30 is kind of when we're going to trickle around, and then we end at 10. Please join us next week when we finish off the indexing section of the chapter 9, and we might even start covering chapter 10 immediately. So thank you all for joining. Have a great night, and I will see you next week.